All right, so now let's do a buffer overflow here. There's this thing you can download. It's a zip file, then you have to unzip it. And then you get this program called Secret. So it is already compiled, and you don't have the source code, or at least I don't think you do. Maybe it's in that main.c, but anyway, here's your function. You can guess a number, and it tells you you're wrong. But if you put in long data, 1, 2, 3, 4, then you get a segmentation fault. So there is some kind of buffer overflow in here. All right. And so here you see part of the source code is available. So you'll see here's the main function. You have a guess, and there's a buffer of 12, and you scan into that buffer without restricting the input. Oh, I think the terminal is hidden by my photo bubble. Thank you for telling me. Good, let me fix that. Good. All right. Thanks for telling me. All right, and make it a little smaller, in fact. Good, so maybe less of that happening. Good, I appreciate the tip. Anyway, so here's the function. There's a possible buffer overflow out here, and there's an end game where you win, but there's no way to get there. So if we can exploit this buffer overflow, maybe we can get there. Although, I usually have trouble exploiting that kind of thing in the main function. But anyway, good, let me know if that happens. So now, let's try this. Let's debug this thing. And before we do this, I'm going to copy that long string so I don't have to type it again. Copy. Okay, so now I go into the debugger and I turn off the colors that irritate me. And then I run it. It asked me for some data, so I put in that long stuff, and then it crashes. And I didn't get what I expected here, which is a little disturbing, because I have to have more. See, I have to have K's and L's here for it to really crash. See, it crashed, but it crashed in some weird way. It's not obvious what the problem is. So I just need a longer exploit string. So let me just run it again and say yes. And now I'm going to put in this, and I'm going to keep going. K, 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 L, 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 L. There, see, this is actually very important. Here, I think what happened is, here I overwrote the saved base pointer, but not the return address. So if you overwrite the saved base pointer, the program will crash, because it's going to try to use an invalid memory address, but it's not giving you direct control of the instruction pointer. But if you put in enough data that you hit the instruction pointer, then you'll actually see information appear. And I still don't think I'm getting what I expected to. A, B, C, D, E, F, G, H, I, J, K, L. I should see R. Oh, okay, it's crashed. And let me try examining info registers and see what's in the RIP. It's here. Yeah, that's what troubles me. I still didn't get what I expected to get, which is pretty screwy. I should have seen this. Secret. Let's see if I'm doing something wrong here. I'm in secret game x86-64, and I'm running secret. Well, my demo is failing, and I'm very confused. I mean, I prepared this like last week, and it's the same machine I prepared it on. So how did I manage to have something go wrong here? Run. Well, my demo is failing. I'm going to have to try again. I don't know what happened. I am confused, although I must say I did not expect this to work, because in general, Buffer overflows from the main routine are hard to exploit because returning to the operating system is handled differently, and I think that's what happened here, although I don't know how I ever got it to work before. Okay, I'll have to look into this. We've done buffer overflows before. You know how they work. Somehow it's not work. Oh, yeah, the ASLR, right. Anyway, all right, so I'm going to forget that. Anyway, we should talk about the defenses. Even though my demo didn't work, we'll just carry on. This always happens. All right, so here's defenses that protect you from buffer overflow. Address-based layout randomization runs each process in a random memory location, so when you try to inject an address and jump to that address, you don't know what address to put in. So it stops the normal buffer overflow from working. Stack canaries are a value placed at the end of the stack frame, and they detect buffer overflow exploits. So if you overflow the variables and you start intruding where the stored base pointer and the stored return pointer are, it will detect that you've written data to a block before that, and it will just stop the execution of the program. It knows you've corrupted the memory. So that's valuable. Data execution prevention puts memory permissions on the memory segments. So you have write or execute is the general rule. Every memory segment can either be writable or executable, and therefore, when you read data from the user, that has to go into a writable section, and that cannot be executable, so even if they jump to it, it won't execute. So that's another way to stop the classical buffer overflow from running. And there are also safer C functions to prevent this. Instead of using getS and scanf, you use fgetS with a limit on the size. When you use scanf, you put a number in the format string to limit how much data you read, and you use string n copy and string n cat and string n printf to limit how many bytes you move. This improves the chance of avoiding a buffer overflow, but in fact, it's still very hard to avoid because people often forget about the extra null byte at the end. And like I say, the modern bandwagon, like me, is saying we should probably just knock off C and switch to Rust. It is so easy to make a terrible mistake in C, and Rust is designed to prevent that. So anyway, all right. And so here's safer source code where we're going to have a stored room for 12, and then I only read 12 from here. So that will have won't have this buffer overflow problem. I wonder about the null byte at the end. I'm a little concerned you might be able to read one byte too many, but anyway, you can't read enough extra data to hit the return pointer, so the typical buffer overflow exploit will not happen. Anyway, let's take a look at the cahoots. 7b, which is here. Goes past 12 bytes, does the program just stop? If it hits the canary value, then the program just stops with an error message. But you have to go quite a bit further than that. There's usually stuff in the way. So if you reserve space for 12, you have to put in quite a bit more than 12 to hit the base pointer or the return pointer. It depends on your program, but typically it's like another 20 bytes past. And the canary is placed at the end of the stack frame. So a small buffer overflow you get away with. And this actually is an interesting issue. There's another form of buffer overflow where you never control the instruction pointer. What you do is you put data in one variable and you leak into another variable and change the value of that variable. That's a more subtle kind of buffer overflow, and there's no defense to stop that. And so that just depends on the structure of your program, whether you can do something bad with that. But if you're clever enough, you probably can. You can change the value of other variables on the stack and affect execution that way. But the results would depend very much on the detailed structure of that program. As far as I know, nobody has any defense against that kind of overflow, except to use Rust. Rust, like most modern languages, checks to see how big the data is and makes sure there's enough room to store it before it puts it in there. So none of this would ever happen. All right, anyway, there's good questions. So let's try this. There we go. All right, so where are parameters placed when you call a function in 64-bit code? They're in registers. Like I say, in 32-bit code, you put them on the stack, but in 64-bit code, you put them in registers, because there are plenty of registers, so you can do that. All right, how long is a pointer to an array in a 64-bit system? Your addresses are always 64 bits. Just like in a 32-bit system, the addresses are always 32 bits. The data can be stored at various sizes, but the address is always 64 bits. By the way, I should mention, you cannot use all possible values of those 64 bits. No operating system in current use that I know of actually uses all 64 bits of the address, because that's an unthinkable amount of memory. Nobody has that. So in fact, that's why you notice it all starts with 4 zeros. They only use a small bit of the 64-bit address space. And the maximum amount of RAM supported by operating systems is something like 64 gigs or 256 gigs. Not the, because I think the, you can actually have like 16 billion gigabytes in a 64-bit address. So they don't really implement all the address bits in practice, because there's no reason to do that. Nobody could afford that much memory. Anyway, but the address is 64 bits long, even though a good portion of it is always just a fixed value in current systems. All right, what command shows a file in hexadecimal and ASCII? We used this last time. I think we didn't see it this time because I didn't do the second demo that failed, but yep, some people remembered. XXD does that. XXD shows the contents of a file in hexadecimal and ASCII, so it's really good to look at files that are binary data, not printable characters. All right. All right. Okay, good. All right. Stop this recording.